Okay, so today we're going to be going over arc length and area of a sector. Okay, but before we do that, there's a couple of things that we want to talk about first. Some um, general topics. Okay, just some things that you guys have forgotten that I might need to remind you about. First of all, when we start working with a calculator, the mode your calculator is in is a big deal. Okay, so every calculator basically defaults to radian mode. Okay, so like when you see just a regular scientific calculator, it'll say either RAD or DEG, and RAD standing for radian and DEG standing for degrees. So when we start working problems where that's going to be an issue, you need to make sure you look at what mode you're in. Remember, degree symbol means degrees. No symbol, radians. It is the default. Also, some textbooks and some notes write it as X or a number with a little R symbol. I've seen that twice, and that's the only reason I bring it up, so that you guys, if you do see it, you know that this means radian. Okay? Now, complementary and supplementary angles. This is, again, way back from geometry. Complementary are angles that add up together to 90 degrees. Supplementary angles are angles that add up to 180 degrees. And of course, in radians, complementary is pi over 2 versus supplementary being pi radians. Okay? So there are two angles that share a vertex that add up to either 90 or 180 degrees. And this is something we're going to be talking about later, but I just wanted to reintroduce it. Okay? Now, length of a circular arc length. Let r be the radius of a circle and theta the non-negative radian measure of a central angle of the circle. So again, central angle means the angle itself, its vertex is at the center of the circle with its terminal and initial side in the circle itself. Okay? So the length of the arc intercepted by the central angle is what we call S. Okay? And S equals theta times r. So arc length, the symbol we use is S. Okay? It's also very often what we use for position. When we talk about it physics, we talk about position being distance or displacement, and we use the symbol S, S of t. Actually comes from the Latin called spatium, okay, or space. So we usually, when we talk about distance, we use S, okay, not S for speed. So S is the distance, and specifically the distance around the outside of the circle. So this, from here to here, this distance, that is our arc length, and it's created by the central angle. Okay, and this theta tells us how far that angle measure is, and S is created from that. This equation should look familiar. Okay? Because arc length is a piece of the circle's what? Circumference. So we all know that circumference is equal to 2 pi r, right? Well, the reason circumference is 2 pi r that's because theta in circumference's case is the 2 pi. Because 2 pi means all the way around the circle. So if you want to find the arc length all the way around the circle, the angle is 2 pi. So this arc length equation, S equals theta r, is nothing more than a piece of the circumference. Now, when you were taught this originally, you were taught that you'd have to find the whole circumference and then use a proportion to find a piece of whatever you needed. But now we're saying, okay, we don't need to find the circumference at all. We can just use this equation to find that piece of the circumference. The problem is that theta has to be in radians. That's what makes this more difficult. Is if we use circumference and we use the angle or a proportion to do it, we don't have to change it into radians because we're using circumference equation. Here, theta has to be in radians, and that's what makes it a little more difficult. Okay, but that's why we learned how to change degrees to radians. Okay, so real easy example. The circle has a radius of 4 inches. Find the length of the arc intercepted by the central angle of 240 degrees. Okay, so we're trying to find the arc length from here, right here, starting here, going all the way around the circle. Going all the way around here. So we're trying to find this distance. Okay? As soon as you see they're talking about distance, you know you're dealing with arc length. So we're using this equation. S equals theta times r. Well, do we know what r is? Sure we do. R is 4. Do we know what theta is? Yes, but we know what it is in degrees. So before we can get started using this equation, we got to get theta in terms of radians. So we use our equation. So 240 degrees times pi over 180 degrees. Okay? So this is going to switch my angle from degrees to radians. So degrees divides out with degrees. So we end up with 240 pi over 180. Divide both by 10. Gives us 24 over 18. Then both of those are divisible by 6, which gives us 4 pi over 3. So that is our theta in radians. So we just plug it in. 4 pi over 3. Which means S equals, and when you multiply fractions, you multiply numerator times numerator. So it's 16 pi over 3 inches. And that's our arc length. That's it. Basically, these equations are plug and play. Again, the most difficult part is remembering that theta has to be in radians to move on. So if they give it to you in degrees, you got to change it to radians first. Okay? Easy. And again, here's the solution. Going through. Okay? And again, if you have a calculator, you can multiply the pi in. It's about 16.76 inches. Easy. Okay? All right. Area of a sector. So area of a sector, since we talked about arc length being a piece of the circumference, area of a sector is nothing more than a piece of the circle's area. Okay? And sector, if you think about it, is a portion anyway. If you've ever played any kind of video game or anything like that, when they say, hey, there's so-and-so in sector 2, well, that's an area, right? A place. So that's what we're talking about, area of a sector, a piece of it. Okay, it's not all of it, it's just a piece. So again, r is the radius of a circle, theta, non-negative radian measure of a central angle of the circle. The area created by two radii with an angle of theta is this. And again, relating it back to the area of the circle that we know, the area of circle we know is pi r squared. That is the area of the whole circle. Because again, if we're talking about the radian measure for the whole circle, it is 2 pi. And 2 pi divided by 2 is just pi. So using my equation here, if the area is the whole thing, we'd end up with that. Okay? Now, I am going to give you a different equation to make this easier. It's technically not a different one, but it's just one of those things that'll make your life a whole lot easier. Is I always write my area of a sector equation this way. 1/2 theta r squared. I split the theta and the dividing by 2 into separate because dividing by 2 is the same thing as multiplying by 1/2. And it makes this just a little bit easier. 9 times out of 10, theta is going to be a fraction. And if we write it the original way, if we write it like this, you're going to get a fraction over a fraction, and that tends to freak my students out. So this way I have a fraction times a fraction, and it makes it easier to deal with. Okay? So this is the equation that I would use if I were you. But again, it doesn't really matter. You get the same answer if you know your algebra. All right. So really simple example. circle has a radius of 8 centimeters. Find the area of a sector with an angle of 130 degrees. Okay? So we're finding area of a sector. First thing you should always do when you're doing a problem like this is write down your equation you're going to use. Well, we're using the area of a sector, which is 1/2 theta r squared. Well, area is what we're trying to find. Do we know what theta is? Sort of. We know theta is 130 degrees, but we need it in radians. Do we know what my r is? Yep. My radius is 8. So the first thing we need to do is find theta in terms of radians. So again, changing degrees to radians, we multiply by pi over 180 degrees, which gives us degrees divides out with degrees, 130 pi over 180, divide both by 10, we get 13 pi over 18. And that's our radian measure that we're going to be using. Okay, can't reduce any further than that. So now we just plug in what we got. So 1/2 times 13 pi over 18 times r squared, which is 8 squared. So we simplify this. We're going to get, now remember, when you're multiplying fractions, you multiply straight across. So technically I put the 8 squared over 1 so that I have 3 fractions being multiplied. So in the numerator, I'm going to get 1 times 13 pi times 64 over 2 times 18 times 1. Now I'm doing this for a very specific reason. Okay? Because I can start reducing my fraction here before I start multiplying. So a lot of my students would sit there and multiply 64 times 13 and then the 2 times the 18 and then start reducing. Okay, but because everything, these are just numbers being multiplied and divided, I can actually reduce my fraction this way to make it easier. For instance, 2 divided by 2 is 1, 64 divided by 2 is 32. Right? And then I have 18, which is also divisible by 2, right? So I divide that by 9, and 32 divided by 2 is 16. So now it makes my fraction more manageable. Now I have 13 pi times 16 over 9. And then, yeah, so at this point you just have to do 13 times 16. 208, yep. So my answer is 208 pi over 9. And that is the area. Oh, and we forgot the centimeters squared. Centimeters squared. That's it. Area of a sector. So the hardest part about this whole problem is making sure you remember to change theta into radians, and then just knowing your fraction rules and how to reduce a fraction. That's it.